we are moving to Professor Laurent Matuana, who is with the School of Packaging at Michigan State University, and his presentation today is on adhesion mechanisms in PVC wood fiber composites. The floor is yours.
So good afternoon, so everybody. I know, so I'm starting, I think, a little bit late, but I think I'm gonna try to really do it in 15 minutes. Maybe within the 20 minutes, I think I'm gonna go through all my slides. I wanna talk about the adhesion mechanisms in wood plastic composite, specifically on PVC-based WPC. What I'm gonna say is that over the past 2 decades, there have been extensive R&D work, particularly here in North America, in Europe, and then also in Asia, about these materials. And as a result of that, today, there is no doubt that WPC, PCs have emerged as an important family of engineering materials. That we can see these materials on so many applications. Some of them I'm gonna present here. So we have the, so the decking and fencing you can see here. So in China, so they have been like trial to use this as a wall panel in their houses. Again, I showed the decking. This is basically the preferred application right now. There are railing, so there are so many examples as I mentioned. So there are attempts also to use this material as a roofing, and then also as a siding and cladding. I want to just ask you, I'm using my cursor as a pointer. Can you see that?
They're running behind time, I think.
No, I'm gonna cruise, so I want to give you maybe the time back. I'm just asking, I'm using my cursor as a pointer. Can you see it? Because I have 2 screens. Can you see it?
Yeah, we can see it.
Okay, that's good. Yeah, so it can be used as a siding, cladding, and then I even found out an application in Japan as a highway sound barrier. So, and there are reasons why these WPC are being used in those type of applications. So if well manufactured, here I insist, if the material is well done, that means you are using a proper formulation, you are using a proper manufacturing processes, so the materials come with a lot of attributes. Okay, some of them are related to the durability, so the lower maintenance, so and then there are so many, good attributes for this material. That's why they're being used in this variety of applications. But now, if we compare these materials with, let's say, wood plastic lumber, you compare that with plastic lumber, what you will find out, so although this WPC, so they are superior to the neat plastics, so in terms of cost and also their stiffness, so their strength performance. Here, when I say strength performance, if I look at the tensile performance, if I look at the flexural performance, even the impact strength, so you'll see that WPC has a lower strength performance, so than most of the plastic, unfilled plastic. Here, I showed you application where WPC are used in a similar application as wood, but WPC are also being used in automotive industry. And then there, the impact resistance is very, very important because of, so the bumping or the impact type of, so vibration in the cars. And then why the strength performance of these materials are very poor if you compare to the field plastic, it's well known. So it's due to the natural incompatibility of mixing 2 dissimilar materials. So as I put in this slide, when you are mixing wood fiber and plastic, wood is hydrophilic. So it's a very polar, high surface energy. And then he has a lot of OH group, those, so hydrogen, so those OH, so hydroxyl groups, they tend, so to create like a strong intermolecular hydrogen bonding that prevent them also to so disperse very well, so in the plastic matrix. And then also because of this, so dissimilarity in the surface characteristics, what is happening, so the plastic doesn't wet wood very well. So as a result, so you have a very weak bond between the two. And then how to solve these problems? I started telling you that we have investigated this over, so the past 2 decades extensively. We know how we can really overcome this. And then usually or commonly, we use what we call the coupling agent or adhesion promoter. The mechanism is very simple. So if you take your wood fiber, you treat the surface with this coupling agent. So basically you are converting your hydrophilic surface to hydrophobic surface. As a result, your fiber become more plastic-like. So in other terms, you reduce the surface energy because the reaction is occurring between your coupling agent and the OH group. You reduce the fiber-fiber bonding. And then because your surface became plastic-like, what is going to happen, you're also improving now the adhesion between your fiber and your plastic. So I'm going to illustrate that by an example. You have a wood fiber here, which has a lot of hydroxyl groups. If you use, let's say, coupling agent as a malated polyolefin, so basically a coupling agent is like a bifunctional material. So on one side, so it's going to link to your wood, and then it's going to expose this aliphatic polymer chain. This polymer chain has a similarity to your plastic matrix in such a way that whenever you are processing, under the heat, your malated coupling agent, this ring is going to open, and then we're going to have the formation of 2 carboxylic group. The carboxylic group is going to react with this hydroxyl group through the formation of ester. And then you can see now here the fiber has been modified, but you have a pending aliphatic chain, so on the surface of that fibers. If you mix this with your plastics, polyolefin is the dominant matrix we are using, so PP or PE. What is going to happen under the heat, this part is going to melt, this part is going to melt, and then this is going to favor, so the diffusion and then interlocking when the sample cool down. So by doing this, so basically you create a strong bond between your fiber and then the matrix. So scientifically what that means, if you can take your fiber, hydrophilic fiber, make it hydrophobic, in other terms, you take a polar material, make it less polar, you reduce the surface tension closer to the surface tension of the matrix, you'll have a very good adhesion between the two. And this is an example of the work that illustrates the correlation between the polarity of the fiber and the strength performance. Here I have single materials. We have the pure polymer is polypropylene. We have untreated wood fiber, and then the malated polypropylene treated fibers. As you can see here, the surface energy was characterized. The PP has less surface energy value than the untreated fiber, clearly showing that this is polar, hydrophilic, and this one is hydrophobic. By doing the treatment, as I mentioned, because we grafted those aliphatic chains on the surface of untreated fiber, what we can see, the surface energy is significantly reduced to the value close of the PP. Now, when we mix this PP with untreated fiber, and then treat PP with treated fibers, and then the neat PP, we make the composite containing 30%, and then we measure the strength properties. I have some other properties, but because of time limitation, I'm just focusing on the tensile strength. What we can see, because of poor, when you use untreated fiber, the adhesion is poor, so you see the strength drops. Okay, so when you come over here, you look the difference, they have significantly different surface tension here. So there is a compatibility. But when the fiber were properly treated, the surface tension of wood significantly decreased to the value close to the PP. We saw also it's correlated very well with the strength performance of your composite with treated fiber. Now, as I said, these materials are commercial, so a lot of groups, so worldwide have investigated this. I'm not the only one. We have done this a lot. But what is very striking is, although polyolefin, PP or PE are the dominant, but PVC is also like the second largest plastic that are being used to make these materials. Now, despite the increased knowledge on the fundamental understanding or the fundamental mechanism of governing the adhesion in WPC, if you dig to the literature, you'll find that a lot of coupling agents that have been developed for polyolefin, when you try it to PVC, they don't work. Then the question becomes why? Why they don't work? And then I did a lot of work on PVC. Then I'm gonna just maybe summarize, so my key findings here. So what we did, we wanted to know why the coupling agents like maleic polypropylene, that works very well in polyolefin, when you use it in PVC, it doesn't work. So I did some work using maleic polypropylene. In addition, I tested also 2 other coupling agents. They were silane-based coupling agents. One of them is a dichloro diethylene silane. Then another one is an aminosilane, okay? Because it contained the nitrogen here. Then this one contained the chlorine atom, and then the maleic polypropylene. So I took 40% of wood, I mixed with PVC. We made this PVC composite. So then we tested the samples. And again, I will focus only on the tensile strength because the strength is what I'm interested here. Then the results are shown here. So this is the yield strength of PVC. This is neat PVC, only plastic lumber. And then this is the counterpart, but which contain 40% of untreated wood fiber. And then these 3 here are the treated fibers. What we observe here, as I told you, this is the deleterious effect of adding wood fiber into the plastic matrix. They tend to decrease the strength because of incompatibility between the 2 materials. But when we treated the fibers, here, I used 3 different treatments. What we observe, so although you can see like a slight increase here, but it's not really statistically significant, we saw that only 1 treatment, so almost matched the strength of PVC lumber. The other treatment did not significantly improve the strength of these composites. Again, we wanted to know why. We went through the surface characteristic of these materials, which I show here. So we have the surface tension. If you look at neat PVC, its surface tension surface energy is around 28. The untreated fiber is very high. I already explained this due to the polarity. But if you look at the 3 treatments, all of them, they reduce the surface energy of the fiber to the values closer to neat PVC, but they did not enhance the strength performance. Not all of them improved the strength performance. I go back here. These 2 here, the fiber used in this composite had almost the same surface energy as PVC, but it didn't really enhance the strength of this composite. Only the strength of aminosilane were improved here. You can see like these 2, they have the same the same surface energy, but they don't improve the strength of the composite at the same extent. So now, as I mentioned before, this treatment here significantly improved the performance of WPC when I use polyolefin as a matrix. But here it doesn't work, clearly showing that, the surface tension matching is not really efficient, or it's a necessary condition, but it's not sufficient to improve the adhesion in PVC. The question becomes why now, only this treatment, so improve the performance of the composite. So among the three treatments used in this study. Now, we look at the difference between polyolefin and PVC. polyolefin like PP or PE, if you look at the atomic composition of this material, they have only carbon and hydrogen atom. They are neutral polymer. In contrast, PVC has a chlorine atom. So that means if you look at that because of that chlorine atom, the chlorine atom, it has 7 electron, so in a 7 valence electron in chlorine atom, meaning that if you look at the acid-base, Lewis acid-base theory, PVC is a strongly electron acceptor or an acidic material. So now, if you look at the acid-base theory, interaction between two materials exists only when one material has an acidic characteristic and another one has a basic characteristic. In other terms, you have to have a material, one component has an acidic or an electron acceptor surface characteristic, and another one has a basic or an electron donor characteristics. So what we did, we said, now, can we really quantify the electron donor and electron acceptor characteristic of these fibers? Yes, we did. We used the inverse gas chromatography. Then we came with these acid-base constant. These are empirical acid-base constant to quantify the electron donor and electron acceptor capability of these materials. And then the Ka stand for, so electron acceptor, the Kd donor. So the donor is a base, the acceptor is an acid. So these are the values. If you compare the two, higher the value, that means higher the Ka value, more acidic the surface is, and then the opposite is a base. We can see that PVC, because of the chlorine atom, is an acidic. And then the untreated fiber is an acidic. And then also the two treatment we used, the malated polypropylene, the dichlorosilane, did not change the acidic nature of the wood fiber. But when we use the aminosilane, because of that nitrogen atom, what happened? The surface of the fiber became strongly acidic. So therefore, according to the Lewis acid-base theory, interaction exists only when you have an acid and then a base, surface characteristic of the fiber. So although I'm not showing it here, so we were able to use the FTIR to demonstrate that when the aminosilane was used as a treatment, because of the presence of that nitrogen atom, and then in a PVC, you have that chlorine atom. So there is a strong, formation of ionic bond between the two. And then this is, so basically the sufficient condition you need for when you're using PVC in order to see an improvement in the performance, the strength performance of your composite. So in conclusion, I can say this. The concept of matching the surface tension of fiber and polymer it's a necessary condition when the polymer is PVC, but it's not sufficient. When you are using PVC, you have to develop your modification in such a way that you alter the electron donor and electron basic characteristic of your fiber and plastics in order to create a chemical bond, because the chlorine atom is on the backbone of PVC, brings chemical potential. So therefore, the diffusion and interlocking is not the only maker. It's necessary, but it's not sufficient. In PVC, you need really to create chemical bond in order to see improvement in the strength performance of these composites. Thank you. And then I don't know if you have questions.
Thank you, Professor Matuana.